Good day, everyone. My name is Sebastian, and along my teammates Kaliana and Paran, we will be presenting our project on design and simulation of triboelectric nanogenerators for energy harvesting. Here is the outline of what we will cover on the presentation. Miniature electronics are in great demand due to the high number of portable electronic devices. Miniature electronics require little power, and nano energy is becoming increasingly popular. Triboelectric nanogenerators have gained popularity in this field as they are a clean energy source that can achieve high energy conversion efficiencies, provide high power densities at a low cost and low weight. All triboelectric nanogenerators are driven by two physical effects. The first one is contact electrification, also referred to as triboelectrification, and is the effect that generates static polarized charges on the contact surfaces of the materials. Then, the electrostatic induction comes into play, driving the energy conversion from mechanical to electrical energy. In particular, triboelectric nanogenerators excel at harvesting energy at low frequencies that can be obtained from human motion or from uncharted areas of wind, waves, and tides. Today, triboelectric nanogenerators have achieved power densities of 500 watts per meter squared and conversion efficiencies of 70 to 85%. Some of the current applications include wearable power sources, wave energy harvesting, as well as pressure-enhanced keyboards. On the right-hand side, you can see a triboelectric nanogenerator design for wave energy harvesting. Triboelectric nanogenerators have four fundamental operation modes, where each operation mode identifies the motion that the triboelectric nanogenerator will use to harvest energy. We have the contact separation mode, the lateral sliding mode, the single electrode mode, and the freestanding mode. The materials selected for the manufacturing of a triboelectric nanogenerator will impact its performance. The Triboelectric series is a helpful guideline for material selection, as materials in far ends of the spectrum will provide higher surface charges. While the Triboelectric series serves as a guideline for material selection, the charge affinities of the different materials are not inflexible. Different studies may show variations in the sign and magnitude of the charge affinity of the exact same material. This is because any small change in the experimental setup or any change in the sample can greatly impact the obtained results. For all triboelectric nanogenerators, there is a pair of surface charges that establishes a potential difference across a particular load. That means they have an inherent capacitive behavior, and therefore their output voltage can be written as the sum of two terms. The first term is the contribution due to the capacitive nature of the nanogenerator, and the second term is the open circuit voltage contribution that comes from the polarized triboelectric charges. On the right-hand side, we can see the equivalent circuit diagram for any triboelectric nanogenerator. The following sections on the operation mode and the material properties for triboelectric nanogenerators will be presented by my teammate Paran. In this study, we investigate thoroughly the contact separation mode, both in simulations and prototypes, as it is the most fundamental mode. Therefore, a more detailed description of the system is required for a better understanding. Using Gauss's theorem, we can obtain the VQX relationship for the triboelectric nanogenerator that is shown on the slide. And from here, we can obtain an equation that shows the buildup charge at the electrodes. We can see from this equation that the charge at the electrodes increases in proportion to the surface charge density that is generated by the triboelectric layers. It also increases in proportion to the surface area of the electrodes and in proportion to the relative permittivity of the triboelectric layers. The new set of simulations focused on investigating the discrepancies between the voltages shown in the COMSOL model and the voltage produced by the prototype. The ideal model does not account for glue, even though it is part of the device. Therefore, glue layers in between each tribo material and their respective electrodes were added into the model and simulated. As it can be observed from the figure, there is a small but meaningful reduction in the output, making the voltage drop from around 14 kilovolts to 13.3 kilovolts, causing a drop of around 100 volts. From the theory on the contact separation triboelectric nanogenerators, it is noted that the charge accumulated at the electrodes is directly proportional to the surface charge density that the tribal materials induce. The surface charge density is defined directly by the users in the simulation software. Therefore, when extremely high outputs are being simulated, it's an indication that the surface charge density value must be reduced. The results from the simulation when decreasing the surface charge density are in agreement with the theory. Decreasing this value immediately impacted the overall energy output of the triboelectric nanogenerator. Additionally, there is still a consistent impact when we consider the glue layers into the simulation model. However, the output voltage of the simulation is still greater than the ones obtained from real prototypes. This indicates that the charge density generated by the prototype is actually far smaller than the one considered into the simulation, and thus the input value should be reduced even further. This set of simulations aim to check if the charge tendencies of a material will have any impact on the simulation. Polypropylene has shown discrepancies in different triboelectric series done by researchers. Therefore, it was chosen to operate in conjunction with PDMS. The first simulation assigned the positive surface charge density to polypropylene and the negative one to PDMS. The second simulation inverted these polarities, and the results showed that inverting the polarities has no effect on the output of the simulation. Now my teammates, Paran and Kaliana, will continue the presentation discussing on the electrospinning experiment and 3D printed prototypes.
There are several new technologies in picture, like for the additive manufacturing, like multi-jet molding, delayed ink writing, and selective laser sintering. We studied those, and we used fused deposit modeling for 3D printing, and we used ABS, PLA, PA, and TPE 3D printed material, and for the thin films we used nylon and polypropylene. So we developed 8 prototypes with combination of each material and tested against sliding and contact separation mode. We achieved highest voltage, that is 4 volt, from nylon and polypropylene in both contact separation and linear sliding modes. So one of the drawbacks when we did the hand tapping, the output voltage was not uniform. So we tried to use the mechanical exciter, and we used at 10 hertz and the signal generator output of 2.5 volt. So you can see we achieved uniform signal, the same 4 volt, but it was uniform. And we checked into the power output improvement methods. We came across the grater structure. There are 3 different types of grating structure, like linear grating, rotating disc, and rotating cylinders. And there are the single material, positive or negative grater trench, or there are 2 materials, complementary materials, grater structures. So this is the principle of operation of single material data structure. This has been elaborated in the report. This is the operation principle of positive and negative 2 material gated structure. So this will be helpful to understand the results of our experiment. And so this is our upper substrate of the negative and positive data structure. We used nylon and polypropylene. Those are the nylon layer. There are 8 layers and interdigitated pattern, nylon and polypropylene, placed in 2 millimeter gap on a cardboard base plate. Straight, that is the electrodes, we used aluminium strips with with 10 millimeter width. So with the gaps of 2 millimeter. So every odd numbers are connected to one side, and the even numbers are connected to one side to make 2 electrodes. To make the comparison, we made 2 single material data structure. One is nylon with 4 strips, and other one is with polypropylene 4 strips. And to compare the efficiency improvement of these gator structures, we made the single material flat uh, triboelectric nanogenerators with nylon and polypropylene. So we conducted the experiment at the lab and observed the waveform, and we tried to maintain the uniform force and the rate to uh, fair comparison, and we observed that with the increase of the rate, of course there was an increase of voltage output. Those are the five waveforms of uh, those five specimen. We received the highest voltage, that is 6 volt, from the positive and negative trench with nylon and PP. Observed instantaneous maximum voltage accordingly. So the positive and negative trench, we got 6 volt, and there are other interesting observation, like in the single material trench the polypropylene gave the highest voltage. The reasons are discussed in the report in detail. And all in all, the single material data structure gave us 2.3 times of voltage than the ungraded one, and the positive and negative two material, complementary two material trench gave 5 times of the conventional trench. So there's a huge increase, and this can be understood with the operational theory as well as the movement efficiency when the sliding taken place with the gated structure. And apart from that, there's the concern of the reliability and robustness, that after several repetitive experiments, the material tend to be removed off and these areas, and there are deposited foreign particles, foreign material from the one of material from the electrodes. So those have to be considered in future experiments. So we need to make those layers abrasive resistant. Um,
The electrospinning machine is a device that generates the continuous nanofibers from a solution. A wide range of materials has been used, especially polymers, which are commonly used for energy harvesting. The device consists of a syringe, a burnt needle, and a collector plate. Then a required voltage is applied between the needle and the plate, effectively generating a solution jet from the needle into the collector plate. So the electrospun nanofibers are materials that have high porosity, spatial interconnectivity, flexibility, tensile strength, and high surface volume ratios. They excel in energy harvesting, energy conversion, and energy storage applications. To achieve a better result of electrospinning, the solvent should be selected in a way that the materials are dissolved. A sufficient pressure should be applied to avoid the overhardening of fibers. There should be a balance between the viscosity and surface tension of the solution. Voltage must be high enough to overcome the surface tension, and the distance between the needle and collector must ensure full evaporation of the solvent. There are several parameters that will affect the formation of fibers and their properties. So the first one is solution conductivity, where the solutions with high conductivity generate thinner fibers and prevent bead formations. Second one is solution concentration, where the concentration of electro spinning should be moderate. If the concentration is low, the fiber will not be continuous, and if it is high, it will be difficult to eject. Thirdly is applied voltage. The applied voltage determines the strength of the electric field, causing the jet to stream. Then flow rate and collector distance are similar, where the bead formation is caused if the rate is too low and if it is placed close to the collector plate. So both affects the morphology of the fibers. The dielectric constant should be high enough to provide thinner fibers. If the dielectric constant of the solvent increases, the productivity increases. So after reviewing several papers, we decided to purchase some materials to carry out electrospinning at the Memel University lab. So before we order, we are giving us the final order. We did a research online on the materials, the vendors, the price, and the estimated time since we have a timeline to complete the project. So this is a table which states with the vendors, the materials, and the quantity we purchased. So we ordered polyvinyl fluoride and formic acid from Fisher Scientific of 500 grams and 500 ml. Then we ordered nylon 11 beads from Scientific Polymer for 500 grams. And we ordered dimethyl acetamide and dichloromethane from Sigma Aldrich, both were of 100 ml. And at last we ordered acetone from Amazon for fluorosos. Unfortunately, the dimethyl acetamide and acetone was delayed, and so we have to use a substitute such as dimethyl sulfoxide and acetone, and we borrowed from the Memel University lab. So based on the materials we received, so we took the materials and we were carrying out the experiment in the lab. So firstly, we measured the weight of the powder we required. So we used a weighing balance and measured 1 gram of PVDF, which are need to be mixed with the solvents such as dimethyl sulfoxide and acetone. And secondly, we weigh the nylon 11 beads for around 2 grams, and the solvents which are used to dissolve the nylon 11 were dichloromethane and formic acid. After weighing the PDF powder and the nylon 11 beads, dimethyl sulfoxide, which were taken around 5 ml by a pipette and was mixed with 5 ml of acetone using the same pipette, and then it was mixed with PVDF powder. Then it was immersed in oil where the temperature was set around 15 degrees Celsius and a RPM of 555. So it was left to dissolve in the magnetic steering equipment. Then following up with PVDF solution, we carry out the same procedure for nylon 11 beads where we took 4.58 ml of formic acid and 2.4 ml of dichloromethane and mix up with nylon beads and put the mixture in a vial and place in the same magnetic steering equipment. So after 2 hours, we found that the PDF powder was dissolved and it was in a perfect solution to insert in the syringe. For the nylon solutions, we found that the beads were not dissolved and it was not ready to be poured into the syringe to form a nanofiber. The electrospinning machine was set up for the experimental. The PDF solution was inserted into the syringe. The aluminum foil was installed at the collector plate side. Then the distance was adjusted around 8 cm between the collector plate and the needle. On the syringe side, the flow rate was adjusted to around 1 ml per hour. The voltage applied was around 15 kilowatts. So the electrospinning process was started, and based on the first photo, it shows that the electrode, which is the aluminum electrode, shows there's nothing has been sprayed. And the second photo with the initial stage where the needle has been start throwing the nanofibers onto the aluminum screens. So the experiment was run around 2 hours, and after 2 hours, where as the last picture states that the nanofibers of PVDF solutions. So this was the end of the process for electrospinning, where we use the nanofibers and using a PVDF solutions as a result. For conclusion, basically for things performance, materials and operation modes are crucial. Stimulation is insightful when compared to real prototypes. Stimulation results shows the importance of complete models and highlights that they have a lower surface density compared to theoretical.
Here are the references cited on the presentation. We kindly thank you for your time.